We transition now from the static map of the skeleton to the dynamic engineering of bone tissue. In biomedical engineering, we do not view bone as a rock. We view it as a prestressed, self-optimizing composite material. If you fail to account for its mechanical limits, any implant you design or any training protocol you develop will lead to structural failure. The material science of bone. Bone is a hierarchical composite. It combines the tensile strength of collagen with the compressive strength of hydroxyapatite calcium phosphate. This duality allows it to exhibit for critical mechanical properties. Strength. This is the capacity of the bone to resist applied force without structural failure. It is categorized into ultimate tensile strength, resisting pulling, and ultimate compressive strength, resisting squeezing. Elasticity. Within the elastic region of a load curve, bone can deform under stress and return to its original geometry once the load is removed. This is vital for shock absorption during locomotion. Plasticity. If a load exceeds the elastic limit, the yield point, the bone enters a plastic state. It deforms permanently. In engineering terms, this is the danger zone where microcracks begin to propagate before a terminal fracture occurs. Anisotropy. This is the most critical concept for structural analysis. Bone is anisotropic, meaning its mechanical properties, stiffness and strength, are direction dependent. It is significantly stronger and stiffer when loaded longitudinally along its length than when loaded transversely across its width. Wolff's law. The self-optimizing chassis. In engineering, a bridge does not get stronger just because more cars drive over it. In biology, however, the bioform does exactly that. This is governed by Wolff's law. The law: bone grows or remodels in response to the functional mechanical demands placed upon it. The mechanism: bone cells' osteocytes act as mechanosensors. When they detect mechanical strain, they trigger a chemical signal to deposit more mineral matrix in the area of high stress. Increased loading athletes, specifically those in high-impact or resistance-based sports, demonstrate significantly higher bone mineral density (BMD), because the skeleton upregulates its thickness to handle the recurring force. Decreased loading atrophy. Conversely, if you remove the load through immobilization, a sedentary lifestyle, or microgravity, in space the body identifies the excess bone as metabolically expensive and begins to resorb it. This leads to bone loss and decreased structural integrity. Structural application. Why direction matters. Because bone is anisotropic, its architecture is specialized for the forces of gravity and locomotion. Longitudinal loading. The cortical outer bone is thickest in the midshaft of long bones to resist the bending and axial loads of standing and running. Transverse loading. Bone is most vulnerable to shear forces. A strike to the side of the femur transverse requires much less force to cause a fracture than a load applied from the top axial. As an engineer, you must treat the skeleton as a living smart material. Strength is the goal. Anisotropy is the constraint. Wolff's law is the maintenance protocol. Ignore these principles, and your understanding of human movement is purely superficial. If you want to dive deeper into the mathematical modeling of these stresses, the Bioform Insights series provides the technical data you need. For the next 7 days, the foundational module is available for $2.99, a 70% reduction from the $9.99 standardji. Invest in the precision of your knowledge. Next, we will analyze the specific stress-strain relationships in different bone types. Are you ready to proceed?